Welcome to the viewers. Now we discuss walks, path, and cycle in graph theory. It's a concept what walks is and walks path is. Suppose let us consider a pictorial representation. If G be the graph, let G be the graph, and its vertices is V1 dash, V2 dash, etc. etc. And edges be V dash is a set, that's a graph with vertices. V dash is a non-empty set, V1 dash, V2 dash, etc. And edges may be empty, E1 dash. Actually, consider here E2 dash in this way. Now let us consider the pictorial representation here, like V1 dash, V2 dash, V3 dash, V4 dash, and V5 dash. If we consider here E1 dash, E2 dash, E3 dash, and E4 dash, then we can say that if defined as a walk W, there is a alternating sequence V1 dash, next to edges, vertices and edges, E1 dash, next, V2 dash, next, E2 dash, next, V3 dash, next, E3 dash, next, V4 dash, next, E4 dash, then V5 dash. So in this way we find, if we find an alternating sequence of vertices and edges, and in such a way that endpoints of EI are the vertices of Vi and Vi plus 1. That means endpoint of EI here, endpoint that is E dash 4, endpoints of EI are the vertices. That means here are the vertices of V4, V4 dash and V5 dash. That means endpoints. Edges of these are that endpoints of EI. Here we find. We consider here edges, endpoint of EI, that is VI, V dash 4 and V5 4. So if we consider here and generalized cases, we consider in cases of a walk, that this endpoint must light, that is endpoint of EI are the vertices of Vi and Vi plus 1. By the induction method it's clear. Here it is E4, so I equals to 4. So here V4 plus V5, here V4 V5. So finally we get some of the idea about walks. Now for the generalized definition, if we consider, that's for how to define it. Let, it is a part of definition, let G be a graph and U dash V dash belongs to V dash G vertices of G. Then we find and alternating sequence, we consider W dash equals to U dash that is equals to v1 dash, starting alternating sequence, if we consider here u dash, u1 dash, v2 dash, e2 dash, in this way, vn minus 1 dash, en minus 1 dash, vn dash, en dash, and vn plus 1 dash, that will be final v dash. That's the end of vertices and edges of G is said to be work such that endpoint of EI dash are the vertices of Vi dash and Vi plus 1 dash. Here I equals to 1 to up to n. For I equals to 1 to up to n. In this way we find the walks. Next, length of the walk. So length of a walk is the number of occurrences of edges in a walk sequence. So here the number of the edges, occurrence in the edges is a walk sequence. So here the length of the walk, how many edges are there in this given representation of pictures? 1, 2, 3, 4. So here the length of the walk is 4. And it's clear that length of the walk is 4. If we consider it as figure 1, so the length of the walk, the length of walk in figure 1 is 4, since there are the 4 edges, 1, 2, 3, 4. So length of the walk is 4. Now we consider the subwalk. If W dash be the sequence like this, V1. Okay, here we taking the same notation as the first bracket in the earlier cases, just a first bracket notation instead of second bracket in all the cases, changing our bracket system. Now here W dash, that will be V1 dash, U1 dash, V2 dash up to En dash and Vn plus 1 dash be a walk in a graph G, then there is a subsequence of consecutive entries W1 dash, if we consider, that is V1 dash, U1 dash. Now if we consider here a generalized notation, W1 dash, that is Vi dash Ei dash Vi plus 1 Ei plus 1 dash Ek dash and Vk dash Ek dash and Vk plus 1, such that 1 less than I less than K less than K plus 1. And okay, it will be n plus 1. Finally we getting the sequence here, n plus 1, and that start and end at a vertex. Is called subarc. So here we find, just to consider here is a walk of a graph, and we find the subsequences like this, and this starts and ends at a vertex is called a subarc. We find it's a subsequence, nothing but. And now if we consider with the pictorial representation like this, v1 dash, v2 dash, v3 dash, v4 dash, v5 dash, v6 dash, in e1 dash edges, e2 dash, e3 dash, e4 dash and e5 dash. If we consider as a w dash, will be considered as a walk, v1 dash, it is a walk, e1 dash, v2 dash, e2 dash, v3 dash, e3 dash, v4 dash, e4 dash, v5 dash, e5 dash and v6 dash. And if we consider another system, w1 dash, a subwalk, v1 dash, u1 dash, v2 dash, e2 dash, v3 dash, e3 dash, and here also another subwalk, w2 dash, v4 dash, e4 dash, v5 dash, e5 dash and v6 dash. And we also say a subwalk is also a walk. This is a property. Now close walk and open walk. A walk w dash, that is u dash, v1 dash, u1 dash, v2 dash, e2 dash, in this way, vn dash, en dash, vn plus 1 dash, that will be, if we consider here u dash equals to v1 dash and vn plus 1 dash, that will be equals to vn dash. Then from u dash to v dash is said to be closed walk if u dash equals to last end point, that is a n plus 1, that is a v dash simply, not vn dash. We consider here v dash, not as a sequence, but here vn dash is there, that's why we only say v dash, u dash and v dash. That is our consideration. If u dash equals to v dash, then we call it a closed walk, and open walk if u dash is not equals to v dash. Like this, if we consider a pictorial representation, just as same cases, v1 dash, v3 dash, here v2 dash, v1, v3, v2, v3 dash. Here we consider v4 dash, and here if v5 dash. Then if we consider here e1 dash, that is e2 dash, it is e3 dash, it is e4 dash, it is e5 dash. Then we consider this walks w dash is equal to v1 dash working sequence, that's alternating sequence, u1 dash, v2 dash, e2 dash, v3 dash, e3 dash, v4 dash, e4 dash, v5 dash, e5 dash. Then finally find v1 dash. So initial and final points are same, so it is a closed walk. So w dash is a closed walk. And if we consider here v1 dash, v2 dash, v3 dash, that's a walking sequence, e1 dash, e2 dash, that's a e3 dash, e4 dash, that is a v5 dash. If we consider as a w1 dash, this walk, v1 dash, e1 dash, v2 dash, e2 dash, v3 dash, e3 dash, v4 dash, e4 dash, v5 dash, then it is not the same. So since v1 dash and v5 dash are not same, so w1 dash is a open walk. So in this way we find the idea of closed walk and open walk. Now we get some of the idea about the concatenation of two walks. How to define it? With the pictorial representation, at first we consider G with a graph and consider as the earlier P requisitions, vertices, edges, etc. etc. All P requisitions have to be considered. Now v1 dash, v2 dash, v3 dash, v4 dash, v5 dash, v6 dash, in this way, and v7 dash, e1 dash, e2 dash, e3 dash, e4 dash, e5 dash, e6 dash. If we consider here v7 dash, Now these two works, if we consider W1 be the work with V1 dash, E1 dash, V2 dash, E2 dash, V3 dash, E3 dash, V4 dash. Another W2 dash, that is V4 dash, E4 dash, V5 dash, E5 dash, V6 dash, E6 dash, V7 dash. Then concatenation of two works are given by W1 dash, W2 dash, that is V1 dash, U1 dash, V2 dash, E2 dash, V3 dash, E3 dash, V4 dash, E4 dash, V5 dash, E5 dash, V6 dash, E6 dash, V7 dash. So the concatenation, we are get some of the idea that if a graph we considering these two works B, another works from U to V such that one path started and one end. So we have get some of the idea with the examples and how to find out the concatenations of two works. And now we are getting some of the idea about trails. What is trail? If all the edges in the work are different are known as trail. That is, trail is a work with no repeated edge. And a trail is closed if starting and terminal vertices of the trail coincide. Then we call trail is a closed. Now a path. A path is a trail which has no repeated vertices except possibly the starting or initial, possibly initial and terminal vertices. If the initial and terminal vertices of the path coincide, then it is called a closed path. And the length of the path is the number of the occurrence of edges in the path. And now if we consider the circuit. What circuit is? A non-trivial closed trail is called circuit. That is, a circuit is non-trivial closed trail. That is, so every loop is a circuit, but every circuit is not loop. Now we end our discussions. If you like this video, like it, share it, subscribe the channel. Thanks for watching.